Hello everyone. So in this video, we are going to see the operating principles or how my alternator will operate when the alternator is connected to infinite bus bar and when my alternator is supplying a single load and when two alternators are working in parallel and supplying a common load. Okay. So these three scenarios we are going to see in this particular video. And whenever I say the operating principle of the alternator in these three cases, basically in three cases, I will change the input power. So you can say the points that I'll consider during this analysis. First of all, I'll vary the input power. Um, P input is varying and excitation is varying. So mainly these two scenario I will consider when I am going to analyze the scenario or operating principles of alternator when it is connected to infinite bus and and when it is operating at isolated, when it is operating when the two alternators are operating in parallel. Okay, so let me first consider the infinite bus. Let's say my alternator is connected to infinite bus. So basically, infinite bus is a ideal bus, you can say, and I will talk about the infinite bus bar characteristics. Let's say you have this alternator, it is connected to infinite bus bar. This is my infinite bus bar, and it has reactance or synchronous reactance between generator and the you can say the infinite bus bar. It is JXS. Here I am not considering any transmission line reactance and all. So you can just consider I have just clubbed all of the inductance here, like leakage inductance, armature reaction inductance, and even if there is inductance of the line, that also I have incorporated in the XS. Okay, and I am neglecting the RS, the synchronous resistance and line resistance and all. And here I have this internal induced EMF EF, and this is my terminal voltage VT. And here I have this armature current IA, and this VT is, let's say, it is my in reference and EF. Okay, and my input power is coming from the prime mover, you can say, and that's how my generator is connected to infinite bus bar. Now I want to uh, mention what are the characteristics of infinite bus bar. Characteristics of infinite bus bar. So basically, to see the effect of the change of input and change of excitation on the synchronous generator when it is connected to infinite bus bar, we must know the characteristics of infinite bus bar. So for infinite bus bar, the magnitude of the, you can say, the bus bar voltage needs to be constant, and the frequency of the bus bar is also constant. And when the frequency is constant, that means the inertia uh, uh, of this infinite bus bar is infinity. So mainly these are the three characteristics, and I can draw for you like the bus bar characteristics in graphical way. Let's say you have the infinite bus bar, and let's say you have this frequency of the bus bar, and you are drawing some power. So it has zero droop. That means you can take whatever power you want to take, but the frequency, there will not be any variation in the frequency. Let's say you are drawing P1 amount of power, then also the frequency will be F star, like maybe if the what do you say, the rated frequency you have. Even if you are increasing the load P2, then also you are having the bus frequency as constant. Okay, even if you inject some amount of active power in the grid, uh, you are injecting some amount of active power, then also your frequency of the bus bar needs to be constant. This is the characteristics of bus bar. Or let's say this is the active power frequency droop characteristics, and let's say you have droop characteristics of bus voltage with respect to reactive power injection. Like the bus voltage will remain be same, you can say, if even if you inject some amount of reactive power to the grid, or if you draw reactive power from the grid, the bus voltage magnitude will still be constant. So here I can show in this way, even if you injecting some amount of reactive power to the bus, then also frequency will be constant. And if you inject reactive power into the infinite bus bar, then also your voltage will be constant. So these are the characteristics of infinite bus bar. This is basically an ideal condition, you can say. Now we will see what will happen if we increase the input power to the synchronous generator when it is connected to infinite bus bar. Okay, so let's come here. You have this generator connected to infinite bus bar. This is my J axis, and this is my EF, and this is my VT, and input power is coming from here. Okay, and this is my IA. Now if you write the equation, so EF is equals to VT plus JXS IA. Okay, now uh, this particular entire system is basically lossless. You can say this is a lossless system. So whatever power you are giving to the synchronous generator, the entire power will go to the grid. Okay, and if you increase the active power through the prime mover, then we will see what will happen. Okay, now we know the active power, how the active power flows. Basically, in case of active power, P is basically EF VT by XS sine delta. Okay, now if you are increasing the input power from the shaft side, from the alternator shaft or prime mover input, basically your terminal voltage is constant, your XS is constant, and you are also not changing the field excitation. So this is also constant, let's say. So your delta needs to be increased, right? Your delta needs to be increased to pump the increment of active power to the grid. So let me consider the if case one here. uh, P input is varying. If my P input is varying, like the mechanical input power is varying, then if my P input is varying, increasing, or you can say, then your delta needs to be increased. Okay, so your rotor angle will you can say will increase, because this EF VT excess you are not even changing. VT you cannot change, excess you are not changing, and even your field excitation is also constant. So this will be your scenario. And if you try to see what is happening actually, maybe you can recall the swing equation of synchronous generator. It is basically M d2 delta by dt square equals to Pm minus Pe. Okay, so this is how it operates. And basically when it is at a steady state, whatever mechanical power you are giving, the same power is going to the grid side, you can say. Same electrical power is going to the electrical side. And uh, if you increase the mechanical input, then at a steady state, these two quantity will same, but we want to see the what will happen in terms of rotor angle variation. So for that, maybe I can consider the rotor dynamic equation. So J d omega by dt, these are the same equation basically, but it will be good to know from this torque point of view also. So this is the rotor dynamic equations, and this is the generated electromagnetic torque, and this is the torque that is coming from the mechanical side, you can say. So what will happen if you increase the prime mover power? That means basically this TL will increase, and what will happen, my rotor will try to accelerate, because if you see the in case of generator, the direction of the electromagnetic torque and the direction of this mechanical torque both are in opposite direction. So if because of my TL load torque, if my generator is rotating in this direction, the electrical torque will try to, you can say, stop, or this electrical torque act as a act in the negative direction, you can say. So my mechanical torque is, let's say, somehow more than this TE, then my synchronous generator rotor will try to speed up. Okay, but since it is connected to infinite bus bar, it cannot speed up. But what it can do, it can change the rotor angle. That's what it can do. Like, to fulfill the energy balance equations, even if you are increasing the active power from the prime mover side, there will be a tendency to speed up of the synchronous generator. But if it try to speed up, then what will happen? The frequency, basically the frequency will change, right? But frequency cannot change because it is connected to infinite bus bar. So the effect of increment in active power will be visible in terms of increment in rotor angle. Okay, so this is how the things will happen. Maybe I can show uh, the rotor view also. Uh, let's say you have this rotor of synchronous generator, and we have this is my rotor, this is my rotor axis, and let's say at t equal to 0, and this is my, let's say, this is my rotating magnetic field, which is rotating as omega s, and this is my rotor which is rotating at omega r, let's say, although this two needs to be same, but want to see the transients conditions. So this particular angle is basically called the rotor angle, and let's say at t equal to 0, my the rotating magnetic field axis was in this direction. At t equal to 0, at some omega st, or after t time, my rotating magnetic field axis rotating in this direction, in this way, omega st. So you have now, this is the total, you can say, deviations of the rotor from the synchronous rotating magnetic field axis at when it was at zero zero time, you can say. So this is your theta electrical. So this is the view actually. Although at steady state your omega r and omega s is nothing but the synchronous speed, and omega r is the rotor speed. These two speed needs to be same because it is connected to infinite bus bar. But when you are increasing the active power, this deviation, like you can say the where your rotating magnetic field is located, this maybe this angle will increase, and this particular axis of the rotor field axis, you can say, it will, maybe it will move further, like as the road, and your rotor will also move like the, like this way your rotor will also move. So this is how the, it will change the rotor angle position, and it will pump the active power to the grid. Okay, now I think it is clear. Now we will see the what will happen if we change the field excitation of the synchronous generator when it is connected to infinite bus bar. Okay, so changing EF. Changing EF means you are basically changing the field excitation. Okay. Uh, Again, we have to take up the help of the previous equations. This is the main operating equation of a synchronous generator. Okay. Let's say in this case, my P input is constant. You are not changing the input power. So whatever input you are giving, the same power will go to the grid, and basically you are changing the EF. So you have P input is nothing but EF Vt xs sine delta, which is a constant term. Okay, and Vt is grid voltage or infinite busbar voltage, which is constant, and xs is also constant. So your EF sine delta needs to be constant. And from the terminal point of view, the terminal voltage Vt, Ia, and terminal power factor of the synchronous generator, obviously it is a three phase, so that also needs to be constant, because whatever power you are giving, the same power will go to the grid. So your terminal voltage and 3 is constant, so your Ia cos theta needs to be constant. So if I draw the phasor diagram for this particular case, basically this case can be easily understood by having phasor diagram. Okay, so let's say this is your terminal voltage of the infinite bus bar. Okay, and initially yeah, you are supplying like, let's say this is your terminal voltage, which is basically constant. This is your Vt, and initially you are supplying power in at a lagging load, let's say Ia, and this is your Ia, so this will be your JIXS. So this will be your JIXS, JIAXS. So if you take the phasor summation, so you will get basically EF. So this is basically your EF. Okay, so this is the case basically, and this is the rotor angle delta, and this is the power factor theta. And if you see the component of Ia cos theta, Ia cos theta component is nothing but this one. So this particular value needs to be constant for constant active power and varying EF. So, and also your EF sine delta. So if you see your EF sine delta component is nothing but this one. So this one is your EF sine delta component. Okay. So this value needs to be constant. Now let's say you are increasing the EF value, and but your active power is constant. So uh, your EF, let's say you have increased your EF here. So this is your EF, let's say EF2 had increased this much, and then what will happen? You now you have this particular voltage as a JIXS drop. So this is your uh, JIAXS drop, and now you have this perpendicular current JIA2. Let's say, let me call it as IA2 axis, and this is your IA2. So you can see your also delta has increased decreased to delta 2. Now what are the things that you have observed here? If you increase EF2 field excitation, you can say, then for constant active power your delta is decreasing and your armature current is increasing. So and also your power factor, operating power factor theta 2 is also increasing. So power factor angle is increasing, so that means your operating power factor is decreasing, right? So your power factor is decreasing. So these are the effect. At increase EF, you have less delta. Less delta means your machine is going towards the overexcitation case, overexcitation, and in case of overexcitation machine, your machine is much more stable. You can say overexcited machine is always have more steady state stability limits as compared to underexcited system. Okay, so in this case, your system stability will increase, although your armature current will also increase, but your power factor will decrease, because you are now delivering excess amount of reactive power to the grid by increasing the field or you can say the induced EMF voltage. As you know, to increase the active reactive power flow, you have to increase the terminal voltage, because reactive power flow depends on the difference of the magnitude of difference of the voltage between two terminals. So here this will be the scenario. So this is how your things will operate when my synchronous generator or alternator connected to grid. Now we will see when my synchronous generator is connected as a isolated operation case. Okay, so isolated case, let's say, that means my synchronous generator is not connected to any infinite bus bar and all, it is operating as isolated generator. Let's say it has a load, okay, jxs, and this is the load something like it can be constant impedance load, constant power load, and constant current load. There are three main types of loads are there. Let's say this is your terminal voltage vt and this is your ef. Now for example, I have this here I have some constant impedance load. So the load I have that has a constant impedance value ZL, let's say. Okay. So what will happen? Uh, this entire, if you look from this point, this particular circuit is acting as a constant impedance. You can say constant impedance. So it will be having some real value or and it will be having some reactance value. Okay. So if you see the armature current IA is equals to EF R plus JX. Okay. Now in this case, if you increase the what do you say? If you increase the excitation, so from this particular equation, you can say your armature current will also increase. And if your armature current is increasing, this terminal voltage will also increase. Okay. And depending on the current, the load power will be decided because load power will be consumed across R. So by increasing your EF, if you increase the EF, then your IA will increase and your terminal voltage will increase and your power like IA square R load power will also increase. So this will be the case if I consider load as a constant impedance load. Okay. But if you consider constant power load, let's say, or maybe in this case, we can think like if we maybe we can analyze something more like if you are increasing EF, in that case, what is happening? uh, your active power is increasing, so you have to increase the active power from the prime mover as well. Okay, because energy must be balanced, so you cannot like from this particular observation you can think like if you increasing the EF and you have the load constant impedance load, then you have to change your field your prime mover input as well because your input power like your output power is also increasing. So to fulfill these conditions, the energy balance condition, you have to vary EF and input power simultaneously. Okay, then only these things can be happen. Okay, and if we consider this load as a constant power load, so this particular load, let's say we I can consider add another slide. So let's say you have this generator, it is connected to bus, let's say it is some kind of bus, some isolated bus, and this is consuming a constant active and reactive power, and this is my J axis, and you have this EF. Okay. Now, as this constant power load is demanding constant power, basically then you are not allowed to increase the input power because if you increase the input power but if but your load power is constant, then what will happen? The extra power this particular synchronous generator is having, that will be like you can say that will be stored in terms of rotating energy, so frequency of the generator will increase. Like you can think from the droop characteristics point of view, every synchronous generator is having their droop characteristics. So this is your P and this is your F. So uh, this is how a droop characteristics of synchronous generator or turbine droop characteristics of synchronous generator look like. Like if you at no load the frequency will be maximum, and as you increase the load demand from the synchronous generator, the frequency will drop. Okay. Now let's say your load demand due to the constant power load demand, you have this much amount of load demand at this active power. Okay, so you are only like because you have to deliver that amount of active power. So you can see at this much amount of active power, let's say I'm calling this a P1. So for this P1 active power delivery, I have this frequency as F1, and this is the nominal frequency, let's say F nominal. Now there is a frequency reduction. Now what will happen if we increase the active power? Now let's say we will see the what will happen. There will be change in the droop characteristics. Okay, so let me draw that one. Let's say this is the frequency, and you are increasing the active power. So the active power input, I should say. So your frequency droop characteristics, you can say like it will be shift. Now you have this. This is your you can say uh, new operating point, and because of the extra input only, the droop curve got shifted, and this is the frequency, and let's say this is your the operating frequency. And as you keep on increasing the input power, although your output power is constant, your frequency, the operating frequency of the system will be tremendously high. Again, if you increase the let's say if you're increasing the frequency, then what will happen? This curve may shift to this point, and again this will be the frequency. If you keep on increasing the input power at constant power load, your frequency curve or droop characteristics curve will keep on shaping towards the upside. And why it is so? Because in case of generator, as I have described, like J d omega by dt is equals to TL minus TE, or we can think this the swing equation also, d2 delta by dt square is equals to Pm minus Pe. If your electrical power consumption is fixed but you are increasing the mechanical input power, your rotor acceleration d2 delta by dt square will increase. Okay, your and it will be like it will be there will be increase in the frequency, and there will be a condition, there will be a case condition when your rotor frequency will be so high and it will be in unstable region. Okay, so that scenario will happen. Or also you can think from this particular equation also, your load torque is constant but your mechanical torque you are keep on increasing, so there will be increment in the rotary speed. So this is how your things will operate, you see, at isolated conditions. So I have considered the constant impedance load and constant current load. Okay, sorry, constant power load. Maybe if you want, maybe I can also consider the constant current load, but it will take some time. But if you want, then I can surely make a video on that. But let me proceed with the operating principle, or how the generator, two synchronous generator will operate when they are connected, when they are sharing a common load. Okay, let's say you have this generator G1, you have this generator G2, and you have this load. Okay, this is my G1, this is my G2, and this is my bus. Here I am calling it as a bus because these two are in parallel, and also here I am considering my load power is constant. Okay, P load, let's say I'm calling it as a constant. Let's say for my case it is 2P, just assumption. I'm assuming my terminal this bus voltage is constant. Also I'm assuming this load power is constant. Okay, in this case basically there can be two scenarios. You can increase the field excitations, or you can increase the input power from the generators. So basically we will first consider, if you consider effect of increment, effect of change in input power. So varying. Okay, let's say you have considered this case. Now tell me one thing, like uh, as I have discussed, like we have the frequency droop characteristics of each generator. Let's say for synchronous generator 1, this is my droop characteristics, and for generator 2, the droop characteristic something like this. Okay, so this is my active power delivery and this is my frequency. Let me increase slightly more. Okay, so uh, this is for generator 1, this is for generator 2. Okay, and here let's say they are supplying, this is supplying some p1 amount of active power, this one is supplying p2 amount of active power, and since I am considering the load power is constant, so my p1 and p2, this is the 2p, so this needs to be same. And here you can see the frequencies. If now let's say I have increased the generator input power of G2. So my P into has increased. If you increase the P input power, then what will happen? Uh, your graph tool simply shift, right? As we have seen the previous slide. So maybe this will be my new curve. Okay, and if you try to see what will be the operating point in this case, uh, say your power. So here, now here you will be having the P1 prime, and here you will be having P2 prime, and your P1 prime plus P2 prime needs to be 2p. Here you can see, in case of increment of input active power from the generator G2 side, it is sharing more power. You can see that it is sharing more power compared to generator 1. Okay, so this is the case. By changing the input power, you can change the bus frequency also. See here, now your frequency got changed from f dash. So this is the main two difference, you can say. In case of when my generator was connected to infinite bus bar, you were not allowed to change the frequency of the bus. But here, by changing the input power, you can change the operating frequency. And these are the group characteristics that generator to generator varies basically. And what will happen, let's say this particular load is demanding 2p amount of active power only, it is not taking any reactive power and all, for as a you just assume. So if you increase the field excitation of this particular generator, then this particular generator operating power factor will go towards the more lagging side, means this particular G1 generator will deliver active and reactive power both, and you are not changing the reactive power EF here, so the extra amount of reactive power will go to the generator G2, you can say. So my generator G1 will act as a source of reactive power, and my generator G2 will behave as a sink of reactive power. So this can be cases like that. And yeah, I hope it is now clear. First, I have discussed what will happen when the generator is connected to infinite bus bar, then characteristics of generator infinite bus bars and all. Then how the things, the delta will change when the generator is connected to infinite bus bar if you change the input power, and what will happen if you change the field excitation uh, when the generator is connected to infinite bus bar, provided the input power is constant. And also we have also discussed like what will happen in case of isolated synchronous generator when the generator is connected to a load. Okay, here also the frequency can vary, like we can see, like if you increase the power input power, the frequency will vary, the frequency will definitely vary. And here also you can see, when at isolated condition, the frequency is not a constant term, it will keep on varying. Okay, so this, yeah, that's what I wanted to discuss in this video. Still, if you have any doubt, you can ask me in the chat. Yeah, thank you.